All right, we're going to look at independence here. So independence, you have a formula up the top, but let's think about what independence means first. So independent events are essentially things that can occur at the same time or can occur simultaneously, but they won't affect each other. So if someone give me an example of what an independent event would be. Think of two things that can happen at the same time. That's the easiest way to look at it. All right, I'll give you an example. So a coin toss and a die roll. You can have both happening at the same time. They won't affect each other, so they're independent. Okay, and if you're a little bit confused with independent and mutually exclusive, I'm going to go through that a little bit later, where I mention how they're different. Okay, so here's an example. It says, consider a trial of a coin of tossing a coin twice. Let A be the event of at least one tail, B be the event of either two heads or two tails, and C be the event that the first toss is a head. Now, I just went through this earlier by writing down all the different parts, and I think what I'm going to do first is I'm going to show you what all the different scenarios are first. So to do that, I'm going to draw a tree diagram. So what should I label on each of these branches? Heads or tails. And then it's two coin tosses on each of these. Heads or tails, yep. All right. So at the end, this is heads and heads, heads, tails, tails, heads, tails, and tails. Now, be very careful. The order does matter on this because if one thing occurs first, for example, if you look at event C, it says the first toss is a head. It's very different to your second toss being a head because the order matters on this. So make sure that you write it in the correct order when you write out part A, which then says list the sample space and the set of outcomes in each of A, B, and C. All right. So looking at A, it says at least one tail. So should I do the first one? No. Second one? So heads, tails. Third one? Tails, heads. And last one? Tails and tails. Okay, B. B be the event of either two heads or two tails. So that's obvious. It has to be either heads, heads, or tails, tails. And C. First toss is a head. How many of those do we have? How many? Two. So it's either heads, heads, or heads, tails. All right. B. Test whether A and B are independent. Now, the first line up there can be used as a test as well as allowing you to figure out the probability of the intersection. So, how many different scenarios do we have? How many outcomes do we have? Sorry, in total, 4. So we have 4 outcomes. So if I was to figure out the probability of A, which has 3 of these outcomes, what would the probability be? 3/4. Probability of B, 1/2, because there's 2 out of 4. All right. Before I actually do the multiplication, I'm going to check what A intersection B is first. So what's A intersection B? So it says it has at least one tail, and then there's 2 heads or 2 tails. So what must A intersection B be? What does it mean? No, what does it mean? I don't want the probability, I want what it means. Yep, you have to have 2 tails because A means one tail, at least one tail, and B says either it's 2 heads or 2 tails. The only scenario that works for is if you have 2 tails. So because of that, your probability of A intersection B will be 1/4, because there's only one of these outcomes. Then if you multiply A and B, you'll get 3/4 times a half, which is 3/8. Because it's 3/8, it's not the same as a quarter, right? So that must mean they are not independent. Okay? All right. C, test whether or not B and C are independent. So we'll do the same thing. Probability of B, we already figured it out. It's a half. Probability of C, how many scenarios are there? 2, so that's 2 out of 4, which is a half. Very good. All right. Probability, what's B intersection C? What does that mean? So B is 2 heads or 2 tails. C is the first toss is a head. What's the only thing that works? Yeah, but what? Hang on. What is B intersection C? What does it mean? Yeah, what's the common thing on them? Heads, right? Heads and heads. All right. So the probability of B intersection C would then be a quarter. If you multiply probability of B with probability of C, you'll then get a quarter, which is the same. So then they must be independent. Fairly straightforward. All right. D, use the additional formula to calculate probability of B union C. Someone tell me what the formula is. Yeah, keep going. So probability of B plus probability of C minus something. B, the intersection, right? So we have B, which is a half, C, which is a half, B intersection C, which is a quarter. So you should get 3/4. Okay? Fairly straightforward stuff. This one will always confuse people because it's not so straightforward. All right. Independent and mutually exclusive. Independent means essentially one thing can occur with the other as well. And their probabilities don't affect each other. Whoops, not. So I gave you an example before, a coin toss and a die toss, okay? Mutually exclusive means one thing cannot occur with the other. What's an example of that? I went through this last time if you remember. Yep. And this one. Is that basic enough difference that you can tell? You can't possibly get a head and a tail at the same time. You can probably get it sitting right in the middle between the coin, however unlikely. However, for independent, you can actually do, sometimes you can do both things at the same time. You can have multiple coin toss, but the probabilities don't affect each other. The mutually exclusive one does, because if you get heads, you can't get tails. So one becomes probable, the other one becomes impossible. Okay? Any questions?